Class 12th, Semiconductor Electronics, Intrinsic Semiconductors. Intrinsic semiconductors or pure semiconductors are the semiconductor crystals which are free from defects and impurities of other elements. The most common examples are silicon and germanium, which belong to group 14 of the periodic table with the electronic configuration as shown here. Now, from the above configuration, we can say that both silicon and germanium have 4 electrons in their outermost orbit. So, now let us see how these electrons can contribute in the process of conduction. For this, consider the crystal lattice of silicon or germanium in 2 dimensions. Now, here you can see that each valence electron of a silicon atom pair with the valence electron of the neighboring silicon atom to form a covalent bond. Now, at 0 Kelvin, all the covalent bonds are complete. Now, what do we mean by this? It means that there are no free electrons available for conduction. And that is the reason the intrinsic semiconductor acts as an insulator at 0 Kelvin. However, the situation is different at room temperature. Let us see how. Now, as you can see in the first diagram, at room temperature, the thermal energy may cause a few of the covalent bonds to break. And when a covalent bond breaks, an electron becomes free. So, if this electron has become free, then the interesting part here is that it will leave behind a vacancy. And this vacancy we call as the hole. Now, since this atom has lost one electron, so it has got a positive charge, that is plus E. So, the hole is actually equivalent to a positive charge plus E. Now, the electrons and hole created in this way are called intrinsic charge carriers and are responsible for the unique conductive properties exhibited by the semiconductors. Now, what do we mean by this? See, in case of conductor, the conduction happens only because of electrons. But in case of semiconductors, the conduction happens because of electrons as well as holes. See, it is easy for us to understand the motion of free electron. But what do we mean by movement of hole? Let us understand with the help of this second diagram. Now, as you can see from the first diagram, a hole was created here because of this free electron. Or if you take another example, let us say that this electron jumps from here to the hole. Then the hole will be transferred to this side. So, the moment of hole is actually opposite to the moment of the bounded electron. So, in a way, we can say that there will be a movement of free electron which is completely independent and that give rise to the electron current, and then there is a movement of hole which give rise to the hole current, and the total current in the semiconductor is given by the sum of both, that is the hole current plus the electron current. Now, one more thing we have to understand here is that apart from the process of generation of conduction electron and holes, a simultaneous process of recombination occurs. Now, what is happening in that? Sometimes these free electrons also recombine with the holes, and at equilibrium, the rate of recombination is equal to the rate of generation of electron and hole pair. Now, let us look at this conduction on the basis of energy bands. Now, at T is equal to 0, as we have seen in the crystal lattice diagram, all the covalent bonds were complete. That means there were no free electrons. And that is the reason if you see this first diagram, all the valence electrons are there in valence band and there is no electron in the conduction band. So we can say that at T is equal to 0 Kelvin, the valence band is completely filled while the conduction band is empty. Now what happens at room temperature? At room temperature, because some of the electrons gain thermal energy, so they jump from valence band to the conduction band. And when they do so, they leave behind the vacancy which we have defined as hole. Now these holes create empty energy levels in the valence band which can be filled by the nearby electrons. That means if this electron moves here, then the hole will be created here. So the movement of the free electrons in the conduction band will give rise to your electronic current, and the movement of the holes in the valence band will give rise to the hole current. So in the end, we can conclude that for intrinsic semiconductors, there are two kinds of carriers, that is electrons and holes. In intrinsic semiconductors, the number of electrons will be equal to the number of holes. The total current will be given by the sum of electron current and the hole current, and most important, an intrinsic semiconductor as a whole is neutral. Thank you.